So for people who like lists of instructions, here's your list. How to predict molecular geometry. First, draw the Lewis structure. 2, figure out how many electron groups on the central atom. Figure out how many bonding groups and lone pairs. And this kills me. Their instructions are refer to table 10.1 to determine the electron geometry and the molecular geometry. Well, that's great if you're doing homework and you have your book. I'm not going to give you that table on an exam. So just scratch that off. Do that, in the beginning. Think about balloons. How would the balloons arrange themselves and then make some of them invisible, the lone pairs? And then look at what you have left. I know there's trigonal pyramidal and trigonal bipyramidal and all those words and stuff, but if you stop and think about it, they are descriptive of the shapes. They were not named to make things hard for us. They were named to make things easier. So look at them a little bit and just get them straight in your head. They'll be fine. So let's do a couple of examples. Predict the molecular geometry and bond angle of CLNO. A lot of people look at this and say, well, carbon and iodine. Especially on an exam, if you're not sure, because like this font doesn't distinguish between lowercase l's and capital I's very well. If you're not sure, ask me. This is chlorine, nitrogen, and oxygen. The way it's arranged is meant to suggest the order in which they are connected. So Cl, N, and O. So we've got 7 and 5 and 6. So that's 18 electrons, right? I already have 2, 4, 6, 8, 10, 12, 14, 16, 18. So I don't have enough to give everybody an octet. And I look at these guys and I'm like, none of these are ones that are going to be happy with an incomplete octet. We're going to have to make a multiple bond. So I'll take this off the nitrogen and share it with the oxygen. Now I've got octets for everybody. Now, to make sure that this is the exactly correct Lewis structure, you'd need to look at formal charges to see whether the bond goes between nitrogen and oxygen or nitrogen and chlorine. Does that matter for determining the molecular shape? No, it doesn't. Because we're not really distinguishing between the oxygen and the chlorine. We're just saying those are 2 atoms. So this is actually how it would be. And one clue to that is looking at the number of bonds that oxygen likes to make. Oxygen likes to make 2. Nitrogen likes to make 3. Chlorine likes to make 1. And so you'll find that this has 0 formal charges. But there's our Lewis structure. How many electron groups are on the central atom? 3. A single bond, a double bond, and a lone pair. Double bond is 1 group. Because this double bond, there's 4 electrons in there. I understand why sometimes you think that's 2 groups. It's 2 pairs. We're not talking about pairs, we're talking about groups. Those 2 pairs of electrons are stuck between the nitrogen and the oxygen. They can't move away from each other. So we have 3 electron groups. How do 3 groups get away from each other? They form a triangle, right? So they're going to form a triangle. And that's called a trigonal planar geometry, right? That's the electron geometry. Thank you. Trigonal planar. That's the electron geometry. What are the bond angles then? 120. But how many lone pairs do we have? We have 1 lone pair. So we need to make this a lone pair. Lone pair is more repulsive. So what's going to happen to this bond angle? It's going to get squeezed. so the actual bond angle is, oops, wrong marker, less than 120. And with this lone pair that's invisible, what's the name of that shape? Bent. So the molecular geometry is bent, and the bond angle is less than 120. This is the electron geometry. Question?
Where's the third electron?
There's a single bond, and a double bond, and a lone pair. So maybe this would help. That's a double bond. So we've got the double bond, the single bond, and the lone pair. Really, really important to get straight in your head what counts as an electron group. One bond of any kind, whether it's single, double, triple, is one group. A lone pair is one group. If you have a radical with a single electron, that's also one group. Okay? Any other questions? Let's do I3 minus. Like, well, that's a weird ion. Yes, it is. So the iodines must be connected to each other. And valence electrons, we have 3 of 7 electrons, and then the negative charge says we have to add 1. So that gives us 22 dots, right? I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. What? I need 2 more electrons. This isn't a case of being short where I need to make multiple bonds. I've got extra electrons. What do I do? Expanded octet. Iodine is in period 5. He's a big guy. He can expand his octet. And so we're going to put another lone pair on the central iodine atom. So how many electron groups? Remember, electron groups, we're just looking at the central atom. We don't care about these guys, just the central atom. How many electron groups? 5. 5 electron groups. How do 5 things get away from each other? 2, 2. We've got, so here's the little girl, and then she's going to have a 2, 2, and one goes back and one comes forward. This is forming a triangle, round, and then this is up and down. What's the name of that? Trigonal bipyramid. It's 2 pyramids stuck together at their bases. Trigonal bipyramid. What's this bond angle? 90. And how about the angle between these 2 guys? It's 120. So we had the axial positions, like the North and the South Pole, and then there was the equatorial. So we've got 3 lone pairs in here. Where are they going to go? These are the big guys. They take up a lot of space. They're very repulsive. Nobody wants to be around them. They're going to go around the middle because then they can get away from each other more. They can have bond angles of 120 around the middle. If we put a lone pair up here and a lone pair here, 90 degrees, that's too close for them. If you try to do that with balloons, big balloons to small balloons, they're going to squish around and give more space to the larger ones. So our lone pairs are going to be in here. So lone pair there, lone pair here, lone pair there. The electron geometry was trigonal bipyramid. These guys are invisible. What's the molecular geometry? Linear. The electron geometry is linear. Now, it didn't ask us for the bond angle, but what's the bond angle? Be 180 degrees. Because we're going all the way would be 180. Any questions? It requires some visualization. It does. This is how to represent these things on paper. This takes some practice. What we usually do is we represent a bond that's in the plane of the paper or the screen as just a regular line. And this hatched wedge is almost like a dotted wedge, is behind the paper or the screen. So we can't really see it, it's behind. The solid wedge is coming out at you. And I think they draw theirs weird. Well, I guess this one's not so weird. But, not what I wanted to do. So that's in the plane, this is in the plane, and then this wedge is coming out at you, and the hatched wedge is going behind. Takes a little bit of practice. I'm so done. We'll finish that later.